Hello, everyone. Today, we begin a fascinating chapter called
The World of Numbers.
What is a number? At first, the question seems simple. We use numbers every day to count objects, measure distances, record temperatures, and describe the world around us. But the world of numbers is far richer than it first appears. Let us begin with the simplest numbers of all. 1, 2, 3, 4. These are the natural numbers. They arose from humanity's need to count. Whether counting cattle, grains, or days, natural numbers provided the first mathematical language for quantity. But mathematics soon encountered a deeper question. What number represents the complete absence of quantity? Nothing. For centuries, this idea remains surprisingly difficult. Ancient civilizations often used placeholders, but they did not treat nothingness as a true number. In Indian philosophy, the concept of shunyata referred to emptiness, a profound state of stillness and completeness. This philosophical idea eventually inspired one of the greatest mathematical inventions in history, shunya. 0. With Brahmagupta, 0 became a genuine mathematical object, governed by precise rules. And once 0 existed, a new question emerged. What happens when subtraction takes us below 0? Suppose you possess 3 coins, but owe 5. How should mathematics describe your situation? To answer this, numbers extended beyond 0 into the negative region.
Positive numbers represented wealth. Negative numbers represented debts.
Together with 0, they formed the integers. The number line now stretched infinitely in both directions. Yet another challenge remained. What if a quantity lies between 2 integers? Half a liter, 3/4 a meter, 5/3 of a journey. Integers alone are no longer sufficient. This leads us to rational numbers.
A rational number is any number that can be written in the form p upon q, where p and q are integers and q is not 0. Fractions, integers, and many decimals all belong to this family. But how do we represent a rational number on the number line? Consider the number 3/4. The denominator tells us to divide the interval between 0 and 1 into 4 equal parts. The numerator tells us to move 3 of those parts from 0. The resulting point represents 3/4. A fraction is no longer merely a symbol. It becomes a precise location on the number line. Now consider another idea. What exactly does the absolute value of a number represent? Think geometrically. The absolute value of a number is simply its distance from 0. Both positive 3 and negative 3 lie 3 units from the origin, so both have the same absolute value. More generally, the distance between any 2 numbers on the number line is given by the absolute value of their difference. Arithmetic and geometry suddenly become the same language. Now observe something remarkable. Between any 2 rational numbers, another rational number can always be found, and between those 2, infinitely many more. This extraordinary property is called density. The rational numbers form an infinitely dense network across the number line. Let us now look at rational numbers through a different lens. Decimals. When a rational number is converted into decimal form, only 2 possibilities can occur. Either the decimal terminates, or it repeats forever. For example, 3 upon 8 equals 0.375. The decimal stops. But 5 upon 11 equals 0.454545, and so on. The pattern repeats endlessly. Now ask yourself, can we predict whether a fraction will terminate or repeat without actually performing division? Pause. Yes, but first, the fraction must be reduced to its simplest form. If the denominator contains only the prime factors 2 and 5, the decimal expansion terminates. Otherwise, it repeats. For example, 7 upon 20 terminates because 20 equals 2 squared multiplied by 5. But 4 upon 15 repeats because 15 contains the prime factor 3. A simple factorization reveals the future behavior of the decimal expansion. Now let us reverse the process. Suppose the decimal is already given. Can we convert it back into a fraction? Consider the repeating decimal 0.454545 and so on. Let this number be x. Multiplying by 100 shifts one complete repeating block. Subtracting the original equation eliminates the repeating part. The result is 99x equals 45. Therefore, x equals 45 upon 99, which simplifies to 5 upon 11.
The repeating decimal was actually a rational number all along. At this stage, rational numbers seem incredibly powerful. They are infinite. They are dense. They seem to fill the entire number line. But do they? Pause. Consider a square whose side length is exactly 1 unit. By the Pythagorean theorem, its diagonal has length square root of 2. Can square root of 2 be written as a fraction? It is irrational. Irrational numbers are numbers that cannot be written as fractions. Their decimal expansions never terminate and never repeat. Square root of 2, square root of 5, square root of 10, all belong to this fascinating family. And then there is perhaps the most famous number in mathematics, pi. Every circle hides it. No matter how large or small a circle may be, the ratio of its circumference to its diameter is always the same number, pi. Its decimal expansion continues forever without repetition.
Yet, mathematicians discovered remarkable ways to approximate it. One of the most beautiful came from Madhava of Sangamagrama, who showed that pi could emerge from an infinite series. A finite geometric object became connected to an infinite mathematical process. Infinity itself entered the study of geometry. Even rational numbers hide beautiful surprises. Consider the fraction 1/7. Its repeating block is 142857. Multiply it by 2 and it becomes 285714. Multiply it by 3 and it becomes 428571. Then 571428, 714285, and 857142. The digits never disappear. They simply rotate. Numbers with this remarkable property are called cyclic numbers, a hidden symmetry concealed inside an ordinary fraction. Now we can finally answer a bigger question. What occupies the number line? Rational numbers, irrational numbers. Together they form the real numbers. Every measurable distance, every temperature, every physical quantity, every point on the continuous number line, all belong to the real number system.